Swayam Prabha. Digital India. Educated India.
So, this is what my algorithm gives, this is what the exact value was. By the exact value, this is greater than an error parameter. So, you can think of this as A sigma minus phi sigma greater than equals to epsilon into phi sigma. What is this delta now? These are randomized algorithms, right. So, I would say the probability of this is bounded by delta. Or I should not say multiplicative error. So, this is known as a multiplicative epsilon delta algorithm. Now, there are situations where this is very close to 0, then this definition is too strong a definition, right, because this thing will now go up too much. So, for that there is another definition which is known as the additive approximation. So far so good? Okay. Now let us look at a problem like this, which kind of models this network thing. This was a classic paper by Paul Witter around mid 90s, mid 80s, 1980s of the previous century. So, this aptly captures this network router problem. Okay. So, the problem is as follows. So, this router has this traffic going along. So, it has to store a sample of size which is very small compared to the full traffic that has gone by, but the sample should be a uniformly random sample. Now, to draw a uniform random sample out of a sequence of traffic whose final value you do not know, because this router only at the end of the day will know how much traffic has gone past, right. It has a fixed size on its router board, so say of size k, that it knows, but it does not know the length of the stream. Someday it could be 1000, someday it could be 1 million, someday it could be 100 million, but the sample that it has to store has to be a uniformly random sample from that stream. Now you must be appreciating this fact that if it is a probability, there should be something above, something below. Now this below thing, it does not know till the stream has gone past. How can it draw a sample that is uniformly random? You understand the problem and the difficulty of it? Okay. So my problem is sample k is much greater than k. So, k is the size of the reservoir, you might say. So, this is like m, and you have to store some part of it, but that part has to be uniformly random. So, this has to come down to a reservoir of size k, much smaller than m. What do you do? Swap with, see, the first part is easy. For the first k elements in the stream, just copy it, right? So think of an I which kind of loops over this. So I equals to 1 to k, our life is pretty smooth. See an element, put it into the reservoir. I plus 1th element comes. What do I do? Either I have to let it go, but if I allow it to let it go, then never can it be in my sample. So I have to take a few decisions, right? You have to take that decision, because that decision has to be taken now only. Once it has gone past, I cannot take a decision on this. So this is one decision. Do I need to take other decisions? Right, very good. The second decision, if yes, so let me name this reservoir as R. Now, as you have seen for your say quick sort, if you always say that my first element is the pivot, then your life is in problem, right? So, that is why what did you do? You picked the pivot uniformly at random. So, the best thing in here, if I have taken a decision to replace, what I would do is I would pick a random number between 1 and k and then replace that value. So, that will allow me some randomness, so that I can use probability and do some calculations over it. Right, this is like is okay. Replace a random entry of R. Now, what about 1? 2 is easy. What about 1? That also has to be a probabilistic decision, right? I cannot deterministically take a decision whether this has to go in or out. So, with a certain probability, I will decide that this element will get into the reservoir. This is not going to be a deterministic decision henceforth. It will be a probabilistic decision. So, what would I say? That with certain probability, replace this element, or rather put this element into a random entry of the reservoir R. Now, is this making some sense with you? Because till now you were accustomed to yes, no deterministic answers. Now, these are probabilistic answers. I will say yes with a certain probability. Fine. Think of this. The sample that you are going to take of size k has to be uniformly at random, right? Okay. Now, for this element and say for example, an element towards the end, which one you think would be more probable to get into the reservoir? Given a choice, which one would you want to put into the reservoir? Elements towards the beginning or elements towards the end? End. Why? See, at the end, whether you put this or this, is it hardly going to make any difference? Mind you, this reservoir has to be an uniformly random sample. So that means towards this end, whatever is in the denominator, so 1 by n and 1 by n plus 1 with n large looks almost the same, right? So our hunch tells us that the probability should kind of go down as I go towards the end of the stream. Because really I do not know where the stream is going to end, I do not know m. So what I would do is, I would try to kind of make the probability proportional to the reservoir size by the length of the stream seen so far. So that an element in here comes with a probability of k by I and an element there comes with a probability of k by m. Mind you, there is obviously always a chance of this element to get into the reservoir, and I am not ruling out that chance, but I am making it get into the reservoir with a cost, because if your stream length is very big compared to k, the probability of this element to get into the reservoir is small. So it perfectly makes sense to makes this probability as k by I, where I is the length of the stream seen so far. We will see if our hunch translates into a correct mathematics. That obviously we need to prove. But this intuition kind of may be working. At least this probability should be variable, that much you understand, right? So the variability I bring in through the stream length. The numerator keeps fixed at k. Okay. So my algorithm is as follows, pretty simple algorithm, we will then analyze it. So, what I would do is, so is the algorithm clear? Professor, I might overshoot by 5 minutes, I think, yeah. So, is the algorithm clear? Think of writing a program for this. If you have to write a program for this Uddalok and Devor should tell you later, how do you do this is very important, right? Think of this, when you write a program, earlier it was just choosing xi to be in the reservoir or not. Now you are being asked to make this decision with a probability. So, think of a subroutine that given this element xi and the probability k by I takes a decision whether, see, finally what is happening is deterministic, either this element is going into the reservoir or not, but the decision in itself is probabilistic. Think this over. How do you write a program to implement this? Fine? Okay. So, say for example, now you have a black box which kind of with the probability k by I can decide whether this element xi is going to replace or not. So, this black box has fixed that probability and given you the decision whether xi is going to replace, get into the new reservoir or not. Once that decision is taken that you are going to replace, which was a probabilistic decision, then you have to fix which random entry of the reservoir to replace. You again need a subroutine for that. So, that is done, right? Okay. Now, how do I prove this result? Because see, I do not know the end. But somewhere down the line you will say that all packets have gone. So, the best bet of proving this is I will maintain an invariant that at every step whatever is there in the reservoir is an uniformly random sample. So, if I can force this invariance at every step of the algorithm, then it should hold at the end as well, right. So, I will for any integer set t, I will show to you that it is that the reservoir is an uniformly random sample with that probability of k by t to be in the reservoir. Fine. Okay. So, this kind of proofs are known as invariance proofs. What? So, I prove a thing for all steps, for a step and then t runs towards the end. Okay. So, what am I required to prove? Okay. So, I R was the reservoir, I use the subscript T to denote the status of the reservoir after T elements of the stream has been seen. So, I want to prove the following claim and then I would be done. For all t greater than I, probability xi belonging to RT is equals to k by t. Here I is the index of the stream. So, the proof is an induction on T. How I view time? So, T and I is the index that maintains the condition of the loop. So, I runs from somewhere to up to T. So, at your ith thing the element is xi. Now, see, mind you, the algorithm starts by first figuring out the first k elements into the reservoir and then it works, right. So, I will do it for the entire thing. So, I runs from the beginning to T. So, that means if I look at k, the reservoir size, so k can be either in this region or in this region, right. If k is in this region, that means I has grown over the reservoir size, and if it is in this region, it still filling up the reservoir. So, in this region I is greater than k, in this region I is less than k. So, k is in okay. Now, I look into the base case. Mind you, the induction is on T. So, case 1 is if I is less than k. I is less than k. So, I am in this zone. Okay. So, convince yourself that in this zone the base case will be when T is equals to k. Right. So, I am in this zone, sorry, I am in this zone. So, the base case would be when k is equals to T, or rather T is equals to k. And you can verify that the probability of xi belonging to R k should be equals to 1, and that is equals to k by T. For the other case, I am going a bit fast over this, you go back and check yourself. If you have doubts, ask later in the tutorial, or I would be around. So, in this base case will be when T equals to I, when T is equals to I, right. which is also k by t. Now, let us get into the induction step. This is what we are interested in. So, what about an I that is less than equals to t, mind you. So, do not bother about the base cases too much, these are boundary cases. If you go back and read a little quietly, this should be okay. But once the base condition holds, now I have a situation where I is the loop index that is going up to t and my induction is over t. So, I would rather look at t. So, I will assume my induction hypothesis up to t and I would prove for t plus 1. So, I now look at any element x I, mind you my I is less than t, and I have to figure out what is the probability with which x I is going into the reservoir at time t plus 1, but the induction hypothesis is true till R t. R t is the status of the reservoir after the tth element has gone, right. So, that is what I have written. Is this uniformly random condition still holding? That is my question. Now, see, for xi to belong to R t plus 1. So, what is R t plus 1? The reservoir indexed with the time. For xi to belong to R t plus 1, what must have happened? Xi was there in the reservoir. So, that means xi belongs to RT and the new element, the t plus 1th element must not have replaced it. So, I now get into the realms of conditional probability. Okay. This statement is okay with you? That for xi to belong there, it must have been there earlier and not replaced. Fine. Now, I use the chain rule. On the first part, on this part, induction hypothesis would apply, right. My induction is on T, remember. So, on this part induction would hold. Into probability xi is not replaced at time t plus 1 given that xi belongs to Rt. Agreed? This is just the chain rule. Now, my induction hypothesis tells me that this is k by t into conditional probability is a probability that we have proved. So, I can now take complements. So, this is 1 minus probability of this is because of induction hypothesis. Agreed? Replaces and the probability of replacement. So, this should be 1 by k into k by t plus 1, right. I am going to remember the entry that I am going to replace is a random entry. So, that has to be uniform 1 by k, and I replace with what probability? K by I, here I is t plus 1. Now, just see what is this. So, this is for a random entry in R, and this is the probability of replacement. If you work this out, this should come to, that's what, and that's what we set out to prove. So, now you can have a job for a good network company, if you can write that program. It is a nice implementable algorithm with a theoretical guarantee. With your, I am from the days of C, so you are all Python people. In Python, this should be a code this much, 4-5 lines maybe just. Ki Devarshi, 5 lines Python, something like that, yeah, 5 to 10 lines at most. It is that simple, right? But the problem was looking insurmountable at the beginning. I did not know, see, the challenge of the problem was I did not know the length of the string. So, this uniformly at random was not making sense to me. How did that magic happen? The magic actually happened with the choice of this probability. Now, how do theorists actually do this? So, see, when you read the paper or when you read the book is written from the beginning to the end, but mathematicians usually mostly do the other way around. They look at this calculation, right? They get their hands dirty on this calculation, and from there they fix out the probability. If you look at this calculation at the beginning, see, just given this problem and the sense of the algorithm, it would not be difficult for you to write that first line, right? It is just not difficult to write the first line. Once you write the first line, writing the second line is also not difficult. It is just the chain rule. Once you write that, 1 minus writing that is not difficult. Now, this part of the calculation actually fixes that probability k by I. So, you now know that for this to turn out to k by t plus 1, I should get things like this, and that kind of gives you a back calculation idea that, well, if I fix the probability as k by I, then this calculation would go in very smoothly. See, it is uniformly at random, right. So, you know that the numerator should be k. Fixing the denominator was the challenge. The calculation gives you that idea, what should be the denominator. So, what remains is to write a program that does fix that probability, choosing and deciding with a probability of k by I, and this number is going to change, you understand. At the very beginning it is k by, say if your reservoir is k by 10 of size 10, then you are looking at k by 11, k by 12, so on and so forth. So, these probabilities are changing at each step. So, this is kind of your first non-trivial randomized streaming algorithm. Fine.